Okay, so yeah, so I want to clarify. This is again I'm saying because this has not been recorded. So I want to clarify the last comment I made. I don't know whether I made it correctly or not. But what Shishendu asked last time was, let's say I have a field, I have two operations that those satisfy this. Let's say this under class operation, we said it will be a commutative group. Under this dot operation or multiplication operation, except for the zeroth element, it again follows the commutative group properties under this dot operation, under class operation, and there is a compatibility relation between this dot and class operation, that every element of this set has to satisfy. Okay, so that's the thing. And Shishendu's question was, if we add more structure, more, let's say, binary operation, some other structure if we introduce, will that be called a field or not? The answer is actually yes, because if all these properties satisfy, then it will be a field. In addition to that, you might have extra structure, extra theorems you can prove, disprove, or something like that. That can happen, but that will be called a field. Just like a field is of course a group under class operation. Field minus the zeroth element is not zeroth, zero element is a group, is a commutative group under the binary operation dot. Okay, so this is the clarification of the last comment I made. Of course, if one of these properties is not satisfied, then it will not be called a field. Okay, but if as long as these are satisfied and you have some more structure, some more things, then it's not a problem. It will still be called a field. Okay. With this thing, then we move on to our next target, which is the vector space. So let's list it down here. So till now we have learned about groups. Okay, I am not writing down the binary operations and other things. And second thing we learned was field. Okay, and then we came to slightly more complicated structure called vector space. Okay, so all these things we have already learned. And we just in the last time we saw some examples of vector space, two examples of vector space, and we defined what a vector space is. Now, so a vector space, we said, has one binary operation, and it is always defined over a field. And field, of course, we just explained it has two binary operations and it satisfies all these 9 properties or axioms. Okay, so now from today onwards, we'll not. So last time the binary operation or the plus operation in the vector space, okay, we denoted it by plus sign, but it is circle. It was circle, and the multiplication operation with the field element or the scalar elements that we said last time was denoted by star. But from today onwards, we will not differentiate between this, we will not explicitly write this plus and this plus separately. We will write this thing, but from the context, we can understand which operation is taking place. If the plus sign is between two vectors, then it is the vector sum that we are talking about. And if the plus sign is between two scalar elements or field elements, then it is of course a scalar binary operation that we are talking about. And again, as we saw that in the vector space also we had one 0, but this 0 is actually different from the 0 in the field element, because this is an element of vector space V, and this is an element of the field F. Okay, so F here, and then F has. So this was the F, right? So from the context, I think everybody can understand which 0 I am talking about, or which plus sign we are talking about, or which multiplication, this or this, that we are talking about. Okay, so we'll not explicitly write. So all this O plus or plus, which is circuit, will be replaced by plus from today onwards, and star will probably be replaced by dot or nothing. So from the context, we can easily understand which star, which binary operation we are talking about. Okay, so now and we had already 2 examples where we saw that how this vector space business comes into play. Today we will define similar things that we defined in groups. Okay, so one thing that we defined in or we saw in group was subgroups. Okay, so similar thing here will be called subspace. So in the group context, if a subset of a group by itself forms a group or has a closer structure, then we said it was a subgroup. So in analogy to that, in the space, in the vector space context, a subspace is what? If a subset W subset or W subset of P satisfies all the 9 properties that we talked about in the last day, then W will be called a subspace. So it's the same analogy that we have given in the group's case, it will be on a subspace. But remember that the W in the vector space case, what happens, W is a subset, it might be a proper subset, or it can be same as V as well, as we saw in the group's case. W. The field it has to take is a full field. Okay. So W is a subspace. We, let's say, what we overlook is over field A. Is a subspace over the same field, right? So that has to be there. So that is there, and so this I don't think we need to elaborate on. Then we have to we'll define another thing, new thing, which is called, obviously no, linear combinations. Linear combinations. Okay. So let V1 Vn are some vectors. So basically, there are some vectors from the vector space. Then a linear combination is nothing but sum over alpha I di equals 1 to. Let us take some n elements from the vector space. Okay, these are basically some vectors, and we take some where alpha I belongs to. Okay, so linear combination is basically if you take vectors, multiply with scalar and sum it, and of course this will be an element of the V, because we have seen that scalar multiplication with the vector is another vector, and then we sum over all such vectors up to n. So summing 2 vectors is a vector, 3 vectors will again be a vector, and so on and so forth. So this will be finally a vector. So linear combination finally gives us another vector. But one important thing to note is that this n is finite. If it is infinite, then we always cannot guarantee whether this will be a vector or not. Okay. we cannot guarantee, because after the infinite sum, the answer that we will be getting might not be in the vector space. So, so one quick example could be like, let's say if we chose this field to be, for example, the rational field Q, okay, and as we saw last time that a field is a vector space over itself, that we saw last time. Okay, so Q, if it is a field, it can be a vector field, vector space over Q itself. Okay, so now let us take Vi is, let's say Vi is to be the ith decimal exactly place of square root. Okay, so what is the value of square root 2? Let us say square root 2 is 1.414 and so on and so forth, right? And as we know, this is an irrational number, right? And now let us take V1 to be 1.000, V2 to be 0.4000, V3 to be 0. Or maybe we can start the indexing from 0, 1, V2 to be 0.01000, and now you know where we are heading to. Now if we take the infinite sum, we will get square root 2. But square root 2 is not in the cube, in the cube. So if we take infinite sum, we may not always guarantee that it will converge to a vector. Understood this part? So that's why linear combinations are always defined on the finite sum, over the finite sum, because we don't have any notion of convergence or whether this will converge to the same set or not. So that's why we generally it is always defined over a finite sum. This is one side point. So that's the linear combinations, and then we define a span. Okay, so after linear combination, let's say we talk about linear independence. Okay. So let a set A, or let us say W, is a subset of. So W has some elements. Okay. Now W will be called a linear independent set if all subsets of W are linearly. Oh, sorry. Let's forget this first. First, we have to define linear independence over few vectors, right? So, linear independence, let the same way V1 up to Vn, okay, they belong to V1, V2 and Vn will be called linearly independent alpha I vi is equal to 0, I equal to 1 to n implies alpha I is equal to 0 for all for I equal to 1 to n. That means V1 up to Vn, they will be called linearly independent if any other than 0, we cannot combine them linearly and get a 0 vector. That means if you take, let's say, two vectors, they will be called linearly independent if we cannot like scale this down and add up to get a null vector. Then they will be called linearly independent. So technical definition is this, but physically if you want to understand that you cannot like add some non-zero scalars to multiply non-zero scalars to vectors and in such a way that you get the null vector. Then if you can do so, then they are called linearly dependent. But if you cannot do so, and only solution to this equation for given n vectors is only solution is all the scalars has to be 0, then you say they are linearly independent. Okay. And if a subset of W, did I define span? No, not yet. So these are, I'll go through this very quickly because we already have this idea in general. In real life, we use all these things, and subset W will be linearly independent if all subsets of W contains linearly independent vectors. What does it mean? Let us we take a subset of W and we take all possible subsets of this W, and all the subsets will contain some vectors, okay, apart from the phi, all subset except null set, okay. Except null set. And if so, those subsets will have some vectors, and we'll check the linearly dependence or independence condition. If they are linearly independent, all the subsets of W and vectors inside all those subsets are linearly independent, then W will be called a linearly independent set. Understood? So any subset you take the vectors from that, and if they are linearly independent for all the subsets of W, then it will be called a linearly independent set. Okay. This, and then we define the span. Okay. All these things we intuitively understand. These are the technical definition that just I want to touch upon. And span. Okay. So let W is a subset of U. Okay. Span of W is written. Okay, let's write it in this way. Okay. Span W is the minimal subspace that let's not go into this detail right now. Okay, so for all practical purposes, for the finite dimensional sets, okay, the span of W is nothing but all the possible linear combinations, finite linear combinations of the elements of W. It's basically sum over I to 1 to n alpha I Wi such that Wi belongs to capital L and n belongs to, let's say, integer set, natural number set. And alpha I belongs to 50. So that means what is the span of W? You take W, you take any subset of W, you take the elements and all possible linear combinations that you can do, okay, will be the span of W. Okay. And actually the technical definition is this: the minimal subspace that contains W. But for finite dimensional cases, that you can prove that these two definitions are actually equivalent. So that means span of any subset, you take this, any subset which may not be a subspace by itself. Let's say if you take one element only, okay, then that will not be a subspace, right? Because let us say you take only V1 from here, okay, then it may not be a subspace because you have all these operations. So V1 plus V1, if it is not 0 actually, then it will give you 2V1 and which is not inside W, right? Or some alpha times V1 is not inside W. So W is just a subset. But span of W says that you take all the linear combinations and you will essentially get a subspace. The span of W is always a subspace. So for anything, if you take one element and span it, 1, 2 element anything, then you will finally get what? Finally you will always get a subspace. Okay, so that's the thing. And then you come to the definition of basis. Linearly independent a linearly independent set which spans the whole vector space is called basis. So now, in terms of the span and the linear independence, so take a subset of W, independent set, subset W of V that spans the whole vector space, but which also is linearly independent. Take a subset which spans the whole vector space, not a subspace, not a proper subspace. Whole vector space it has to span, as well as all its element will be such that take any subset from that set are linearly independent, then they are called a basis. And if you actually think carefully, that basis is not unique. That's why it's not the basis, it's a basis. So that subset will be called a basis, and the elements of that set will be called a basis element, and the cardinality or number of elements for the finite dimensional cases, number of elements in a basis will be its dimension. So dimension of a vector space is defined. So all these ideas we have, so that's why I am not giving any example. This is just, so then 6 are what did I say? Dimension dimension is number of element of a basis is called the dimension of the vector space. Number of elements. If it is if the number is finite, then it is a finite dimensional vector space. If it is not finite, then it will be infinite dimensional vector space. So with all these definitions, when we want to go. Okay. So any questions until now? So all these terms you are familiar with, right? Linearly independent, span, and subspace. Subspace, okay, if you know, if you understood the concept of subgroups, then you can understand the concept of like subspace. You can understand the concept of subfield also if need be. Here we are not defining any subfield, or we don't need it. But so any structure, and if subset of a structure follows the same property under the same operations, then there will be a sub that object. Nothing else. So that you understood. Of course, this span, linearly independent set, basis, and all these things also you, I think, understand. Okay. So now another thing that we introduced, and that will be the last topic of today's class, today's talk, and then from next downwards we'll go to the definition of linear representations. Okay, so it's in the kind of similar line of groups that we defined groups and then subgroups, and then we came to an important concept called, what was the last topic in the group? An important concept called homomorphism, right? In the group context, when we were studying groups, we saw that between two groups, let's say I have a group G, another group H, and if we can give a map from this G to H, okay, and if this map satisfies G1, G2, let's say star operation is equal to f of G1, let's say the operation is dot here, then we call if a homomorphism. Okay. So what is the importance? Importance was that it is kind of a structure preserving map. So whatever structure I had given to G or was there in G, the same structure, it might shrink a bit, but the same structure will be followed in the group G. Okay, so that was the thing. The same concept we will be applying here. So now let us look at, so here also we try to come up with maps, okay, the similar thing, so a function from a group to group. So in this case, let's say if we want to define, or if we want to try to give a, let's say, map from one vector space to another vector space. So let us say we have two vector spaces. Similar analogy, okay, we have two groups. Let's say we have two vector spaces, okay, and we want to define a structure preserving map. Okay, so in the vector space, what were the structures? There were basically two structures. One was the plus operation from vector space to this thing. What is the second structure that we gave? was a dot operation or star operation. These were the two structures that was inbuilt in a vector space. And now, in the similar vein, as we define homomorphism in the vector in the groups, okay? In the similar vein, we want to give a mapping from one vector space to other vector space. So this we want to give. Then, in order to preserve the structure, what should be the criteria in our case? In the vector space. Let us call V to W. We want to preserve these two structures. In the groups, there were only one structure, one binary operation. So this group had a binary operation, this group had a binary operation, and we wanted to preserve the structure. That's why we put this condition in order to call it a homomorphism. But here also, let us say similar thing we want to give here.
These two vector spaces are on the same field.
Yeah, that is the first question that we have to ask, that whether they are on the same, over the same field, they are defined over the same field or not. This is the first question you have to ask. Yes, so one condition has to be that they, so if the V and W are two vector spaces. We stopped here, but the first important question we have to ask, over the same field. So first condition would be they have to be defined over the same field. It does not have to be. If let's say we can give some structure preservation from this field to the new field, then, but that's a little bit complicated. But generally what in the homomorphism of this kind, what we say that they are defined over the same field in case. Now let us say they are defined over the same field. Then what are the structures that we want to preserve? The structures are essentially this. So if we want to preserve this structure, what will be the criteria? V1 plus V2 has to be seen as V1 plus. So we want to preserve this structure. So of course this plus and this plus is defined over V and this plus is defined over W. Right? They are in general different, so that is the condition that we have to put. Another structure that we want to preserve is the second condition. Okay, so this is one structure, second structure, alpha times V should be equal to what? Alpha times. Right. For all V, V1, V2 belongs to capital V, for all alpha belongs to L. Understood? And what is this? What does it call? We've seen these conditions in many contexts, especially in quantum physics, quantum mechanics. Unitary? No, this is not a change of basis. These are linear transformations. linear operator. In physics, we call this type of functions as linear operators. So, in physics, we generally combine these two with a single alpha 1 v1 plus alpha 2 v2 should be equal to alpha 1 a v1 plus alpha 2 a. Usually write in this fashion. We combine these two together into one single expression where alpha 1, alpha 2, v1, v2, alpha 1, alpha 2 are from the field, real number or complex number, and v1, v2 are from the vector space. So they, in physics, we generally call them linear operators. But okay, we'll not be calling linear operators, but these are called linear transformations. Okay, so what is the essentiality of this thing is, then if these two conditions are satisfied, then F will be called a linear transformation. And from C, as we already mentioned, that under this class operation, this is a commutative group. Okay? So this is essentially a group. Okay? Then one property that we saw, that if it is a structure preserving map, at least if this condition is satisfied, it is basically a group property, group homomorphism, which immediately told us in these cases, let us call it each. Oh, this is also each. Let us call it small each. Okay. So in these cases, once we defined homomorphism, we proved two important properties. One was each of E has to be E. Identity element has to map to the identity element. What will be the equivalent in here? So this forms a group under addition, and this is exactly homomorphism under addition, right? And what is the identity element in the plus operation? This is 0, right? So this immediately tells if F is a linear transformation, then F of 0 should map to 0. 0 of this vector space is to map to 0. And what was the other thing? So here the equivalent thing will be F of minus B should be minus of 15. That of course is clear from this also. But even if we remove this condition, then also this has to be satisfied. And these two are actually consistent. This is consistent with this. We don't have a problem. So this is the importance of kind of linear transformation, that it actually preserves the structure of the vector spaces. And that is why when we talk about linear spaces in quantum physics or quantum mechanics, we always generally talk about linear operators. Basically, if we want to go from one Hilbert space to another Hilbert space, we always use linear transformation so that the structure is preserved, and whatever calculation we do in this case, there is an analogous thing for the upper space. Okay. So that's or maybe from the same Hilbert space to same Hilbert space, linear operators we can define from the same Hilbert space to same Hilbert space. Usually in quantum mechanics we have only one, not only one Hilbert space, and we give the linear operators maps from same Hilbert space to same. And nowhere it, so just like the earlier cases, as we saw that if we give maps from all the elements to the identity element, that is also a structure preserving in this sense. Okay. So in that case, so what will be the equivalent thing here? It will be all the vectors we can map to the zero element of the other. And that kind of, if we represent these things as a matrix that we just come to, it will be a zero matrix basically. Okay. So now let us give the matrix form of this linear transformation. Let us say we have already defined basis. Let us say V is a vector space, and B, let's say vector space, and B basis is a finite dimensional vector space. With basis, let's say E1, E2, En. So this is, let's say, n-dimensional vector space, and the bases are E1, E2, up to En. And let W, the same thing with is another finite dimensional B vector space. Let's say basis is if R basically F1 to F3. So let's say this is m-dimensional vector space, this is n-dimensional vector space. Basis are E1, E2 to En, and these are F1, F2 to F. Then if is linear transformation. Okay. We want to kind of find the matrix form of this linear transformation. As we saw earlier, that linear transformation or linear operator are represented by some matrices. For finite dimension cases, we are considering finite dimension cases because it may not be possible in infinite dimension to give matrix representation. So that's why we are not going to that. Okay, so I will clear this thing up, but I will write the important things here. So since this is linear transformation, what it has to satisfy are these two conditions. Now, there are two things that we know already. One is, this is the basis, that means this spans the whole vector space. That means any vector from V can be written as a linear sum, linear combination of these vectors. And that is actually unique. Same for W. Right? So, if of course you take any vector from V, it will transform that vector to, it will map any vector from V to W. Right? So, in principle, it can transform E1 also. E1 is a vector of vector space. So, if acting on E1 will give me a vector in W, which in principle I can write in terms of these basis vectors as a linear sum. Right? So let us say they are alpha one F1 plus alpha 2 1 F2 plus dot alpha F1. And this one I have kept because of this one here. This one, this one, this one. Similar. So the argument is clear. Okay, so this is also F. This is also F. It might be confusing. But let's B. Okay. So T. Okay, one thing you will notice that generally when we talk about linear transformation, though it's a function from one space to another space, sometimes we omit these brackets since this is linear. Okay. So for the moment we'll keep these brackets, parentheses, and later on we might come up with a convention where we don't put these brackets, but we always remember this is a function. It takes an argument and gives an output. Okay, but that will be at a later stage. Then similarly, we can take another vector. Let us take the second basis element. Then again, we can, this will be a different alpha, and let's say name it as 1 2 F1 plus alpha A2. So this is essentially sum over I into 1 to n I1 F I, right? En is alpha 1n F1 and so on and so forth n. So these are essentially sum over alpha I 2 Fi. This is alpha I in if I. Or combine this, all these things with what we can write is T E, let's say J is nothing but sum over alpha I J if I equal to 1 to n for all J. And if we remove the summation, if we use the Einstein summation convention, we generally don't write the summation. But for explicitly, for the time being, I'm writing this. Later on, we may remove these summations. And now, let us say, usually in physics or mathematics also sometimes, but let us say I have a vector v. Okay, we usually write a vector in terms of component. What does it mean? Once given a basis, it means, let's say, V1, Vn, right? What it means essentially is nothing but sum over Vi, Ei, where Ei are the vectors. We usually write some hat here. Right? So these are basis vectors, basis elements. So these are the components of the vectors. When we write them in a column notation, these are essentially the components. Right? These entries are essentially the components with respect to that basis choice we have. Right? Then what will happen is let us say under this linear transformation, what is the form? Let us say under this linear transformation, T of course takes this V, will give me some output. Let us say all this is W. But W is a vector in the vector space W. So it has to be expanded in this basis. So let us say this is nothing but Wi if I. Right? Since I can erase this part, right? So T acting on V explicitly raises arrow upstairs so that we understand this is a vector. Okay. And these are scalars, these are components. Okay. So T is nothing but T sum over Vi, Ei. But Ei are the basis vectors, Vi are the components. Okay. Let's say, let's write it as J. Okay. Now, what is the second condition that tells me that I can take? So sorry, first condition tells me that I can take the sum out. So I can write it as sum J is equal to 1 to n. This sum can be taken out from the first condition, first property of the linear transformation. Then the second condition tells me these are components, these are nothing but some numbers or field elements. I mean elements from the field, and in general in our case it will be numbers. But even if it is a field element, then also we know for linearity condition to be satisfied, you can take this out. So then what you can do is in Vj T of Ej. Right? And we know how Ej transforms. So there will be another sum, J is 1 to n, I is 1 to n. This will be Bj alpha ij and fi. And fi are the basis elements. Or if we define it to be Wi after the transformation, so it is nothing but Wi fi. And then we can identify how Wi is called. So Wi, the relationship, the component that we will be getting after the transformation, linear transformation, is nothing but alpha ij bj. So that is what, and this is essentially the matrix form of this transformation alpha. This transformation T. This is nothing but the matrix So with the linearity property, we have shown that any linear transformation can be actually written down as a matrix of A plus B. And now if it is from V to V itself, then it will be a square matrix. But nowhere it is guaranteed that this has to be invertible matrix. Because, for example, if you take the transformation to be, let's say, to be the transformation which takes all the element to the zero element, then also it's a linear transformation. But matrix form corresponding to that will be basically all the elements of the matrix to be 0. In that case, it will be 0, 0, 0, 0, all zeros. Okay. So linear transformation, nowhere it is guaranteed that it is always invertible. But it guarantees that if the transformation is between two finite dimensional spaces, it will have a matrix form. So that we can guarantee. And this is, and the same here. If it happened to be a bijection or invertible, then it's called isomorphism. It's the same name. Okay. So if T is a bijection, then T is called an isomorphism. So kind of we, and in that cases, in the bijection cases that we know that we can invert it further. So one thing that you can go and check that if it is a basis transformation, okay, it is a linear transformation. Basis transformation means a linear, invertible linear transformation. And in that case is what will be the form of this that you can determine. So we often call that this is a basis transformation matrix, and what is the form of that that you can actually get from the similar analysis. So that's the thing. So today maybe this is a good point to stop. So time 8 o'clock. Okay. Okay. So what we learned today is from the vector space, what is a subspace, and then we define linear independence, then we define the span of the vector, and then we define the basis vectors, and from that we define the structure preserving map, and we can guess what should be the condition for the structure preserving map, and what are they called, this structure preserving map in the vector space. They are called linear transformation. And for a linear transformation for the finite dimensional vector spaces between two finite dimensional vector spaces, we can get its matrix form. So that's the thing. And then, and if these linear transformations are happen to be a bijection, state-wise bijection, then they are called invertible, and this has a special name called isomorphism. Okay. Stop this here.